Hi, everybody. Thanks for coming. It's a long list of stuff and a long list of collaborative places that I work. You're probably wondering, why would anybody in their right mind do that to themselves? And the reason is because, as Dan said, I'm interested in water and health issues, and I'm interested in um, this trail from surface water uh, to actual to really from land use to surface water, from surface water to drinking water, from drinking water to people, to good health. And with a side detour, as Dan was kind of saying, a side detour relative to sentinel organisms, and sentinel organisms, really aquatic animals, really fish, being used effectively as canaries in a coal mine, as animals that can give us uh, um, a preview of the potential toxicological exposures that we may be exposed to relative to water quality. So that's kind of what I'm interested in. And what I found over time is that the nexus between UNL, IANR, Doherty Water for Food, the College of Public Health, and UNO, that nexus has been really productive in that it allows me to talk to a number of people and interact with a number of professors all over the place that are doing really cool things. So it kind of expands my overall worldview, which is really, from a professorial perspective, really valuable. Now, if I'm going to talk about this, and when I was coming up with these slides, I started down this road, and I thought, well, one thing I used to say is that these linkages are sometimes really tenuous, and it's really hard to take surface water and relate it to an adverse health outcome. Can't say that today. How come? Because of Flint, Michigan, right? Flint, Michigan is a pretty easy cascade from water, from raw surface water to adverse effect. So we start off in Flint, Michigan, just real briefly. We start off in Flint, Michigan with polluted water. The water in the Flint River has 8 times the salt, 8 times the chloride ions, Cl minus, 8 times the chloride that does Detroit drinking water. Detroit drinking water is pulled from the depths of Lake Huron, so it's fairly clean. The water from Flint River is salty. That salt corrodes the pipes. The pipes in Flint, Michigan are lead pipes soldered, or excuse me, I said that wrong, iron pipes soldered together with lead. So that salt corrodes both the iron and it corrodes the lead. The corrosion of the iron is a problem because the water that is coming in is also dirty. Right? The water's dirty, meaning that it's full, in this case, meaning that it's full of bacteria. And those bacteria can be pathogenic. They can cause disease like amoebic dysentery or whatever else. So we need to kill those bacteria. Well, the problem is, and to do that, we put chlorine, Cl2, the gas, right? We put chlorine into the water. Problem is that the iron binds, chelates with the chlorine. So the remediation for the bacteria doesn't work. So people are getting sick. The second thing that happens is the corrosiveness of the salt leads to lead in the water, and children are having neurological impairment. It's a lot of kind of elementary chemistry, water chemistry going on there, but really, and there's also clearly improper treatment, right? What they were trying to do was treat the bacteria, and they couldn't. The problem, though, is it's not really a water quality question. It's a human question. They should have known better. People can go out, take a sample of the water out of the Flint River, and look at its salinity content. And had they done that, they would have known that their treatment wasn't going to work. because what they were finding was certainly nothing novel. So they someone unfortunately fell asleep at the switch, and when they fell asleep at the switch, citizens paid for that, and they paid for that with the neurological health of their children. So it's a really tragic situation. So we have, unfortunately, in the papers today, right, a very clear smoking gun trail between a contaminated river and adverse health impact. As devastating as that is, and it is devastating, if you had one of those children that is now suffering from that neurological impairment that is never going to go away, it's pretty devastating. But as devastating as that is, that's not what I want to talk about today. Flint, Michigan is an example of a traditional water pollution problem. And I want to talk today about non-traditional problems. But let's start with what I mean by a traditional water pollution problem. The problem, and again, I am in no means minimizing the adverse health impact here, because it's pretty severe. But it has a limited geography. It's impacting Flint, Michigan. It's not impacting Detroit, which is a few miles down the road. Limited geography. The environmental problem is fixable. They could have, had they done due diligence, it never would have happened. Had they not gotten off of Detroit water, it would have never happened in the first place. So it's a political problem or a social science problem, and it's kind of cool. I understand that there are people here that are in environmental studies or in ENV 101 or whatever else. I mean, this is poster child for your class, right? Because it's that interdigitation between natural science, the water quality, the chemistry, and social science, the politics of how the communities were dealing with that. Really kind of interesting. And again, none of this was really what I planned to talk about today, but it's so hot in the news that it's kind of hard to pretend that it didn't happen, particularly if you're going to stand up here and talk about water health issues. The other thing, again, is that the biological problem is acute, it's obvious, it's newsworthy, you've got children, neurological impairment, really sad, really devastating. Traditional water pollution problem. But it's not what I'm here. That's not what I want to spend the last 40 minutes talking about. I just burned up the first 10. Now let's talk about something else. Let's talk about a different type of problem. And let's think about, and I'm just going to jump right in. Let's think about agrochemical contamination, right? And what I mean by that is agrochemicals applied, running off, getting into surface water. And we can also further, as Dan was saying before, we can talk about one of my, I guess, burgeoning specialties, which is atrazine, right? Atrazine is probably, many of you are probably aware, atrazine is the second most commonly used herbicide in the world. Roundup, glyphosate is number 1, atrazine is number 2. Atrazine, again, is applied to crops, things like corn, basically grasses, and it kills broadleaf weeds. And when it rains, that can run off. When it runs off, it can get into surface water and ultimately get into groundwater and ultimately get into drinking water. Okay. This has also been in the news. New York Times, 2009, debating how much weed killer of atrazine is safe in our water. Again, 2009, common weed killer atrazine showing up in public water supply. These are some small towns in Illinois, and I have a little bit of data on this that I'm going to show you in a moment. Even if you're a doubter, Syngenta, the maker of atrazine, isn't a doubter. They just paid these communities $105 million in a lawsuit based upon the damages that happened. So the company that produces the compound recognizes the damage. I'm not trying to make a political statement there, it's just the reality of the situation. Okay. These problems, Lazarus is actually a lawyer. He's a lawyer, I believe he's at Cornell, and he came up with this idea of, in modern parlance, right, he came up with this idea of super wicked environmental problems. So I'm not making this up, Lazarus came up with this. And what Lazarus said is, unlike what's happening in Flint, That's not a super wicked problem. It's a really bad problem. It's really sad. It's really devastating. It is not a super wicked problem. What is a super wicked problem then? A super wicked problem occurs over a very large geography. Unlike Flint, Michigan, which was local, a super wicked problem could potentially occur over, again, a very, very large geography. What else? The environmental problem will have multiple sources. The source of the Flint, Michigan problem is the Flint River. The source of nutrients in the Gulf of Mexico is runoff from 100,000, a million different acreages within the Mississippi River Basin. Really, really different kind of a problem, right? That kind of problem, when you have multiple sources of entry of contamination into the environment, multiple meaning hundreds of thousands, if not millions, that and the fact that it's a large geography, that's only fixable with considerable political effort. We could completely the Missouri River leaving Nebraska could be completely clean. Not that that's going to happen, and what I mean by that is there's always going to be sediment. There was sediment back in Lewis and Clark's day, right? But even if it was distilled water coming out, we're not the only state between us and the Gulf of Mexico, right? There's a lot of other states involved. So politically, it's a really tough, or socially, it's a very difficult problem to grapple with. Much more difficult than a single river and a single town pulling water out of it for drinking water. The Flint problem is simple in comparison. Also, the Flint problem, no one's going to say, you know, that child right there who just had a drop of 10 IQ points from this year to last year, I don't believe that that's caused by the water. There aren't really very many environmental doubters that lead causes neurological defect. Is atrazine an endocrine disrupting compound? Is atrazine a teratogen? There are doubters. There are doubters out there. Makes the problem a little bit more difficult to interact with the community, or to interact with the stakeholders when you have those kind of problems. Okay. The poster child for super wicked problems, of course, is global climate change, right? Global climate change, it's happening on a global level. What's contributing to it? Everything. Every car, every chimney, every smokestack, everything. Hundreds of thousands, if not millions of small non-point sources, right? And who's responsible? Everybody. And look how well the Paris talks or the Kyoto conference from a number of years ago, look how well they're doing to solve the problem politically. In other words, they're getting nowhere. It's not that there is some perhaps political inertia. It's also just a really hard, or as Lazarus would say, a super wicked problem to deal with. It's just really difficult. I would contend that contamination within the Mississippi River drainage, Missouri, Ohio, Mississippi rivers, within that drainage system, freshwater contamination is also a super wicked problem. Now, that's not Lazarus talking, that's me. But I would make the argument, vast geography, lots of sources in which contaminants are entering the water system, no real easy political entity that's responsible for that enormous problem. So that's kind of my thesis today. That's my thesis, is that this is the problem. Of course, I'm going to pick on atrazine. I'm only picking on atrazine really for one reason, and I'll get to why that is in a couple of minutes, and it's probably not what you think. But it could be, we could talk about a number of different pesticides. We could talk about nutrients, phosphorus and nitrogen. We could talk about a number of different chemicals, or we could talk about the summation of all of those chemicals together as a mixture and what those chemicals are doing within the river. And again, I picked on atrazine, and I'll tell you why. And it's not just the reason is not because we're the Cornhuskers and there's a lot of corn here and it's used on corn. That's not why. There's another reason. I'll talk about it in a second. All right. Let me show you a little data. So some of you may be sitting here and you may be thinking, okay, well, yeah, all right. So maybe there's these chemicals in the water, but kind of like, so what? Does it really matter, or is it something that we really need to think about? Well, if you live in Illinois, you do. There was a study that came out by the US EPA that has been ongoing for about the last 15 years, where they have been collecting water at 15 different drinking water facilities. Now, this is the incoming water, right? The water coming in, not the treated water, the pre-treatment water. Again, sampling from 2004 to 2011. My students and I was going to say my students and I, but that's a lie. I didn't do it. My students did it. My students took this massive data set and they made it orthogonal. All right. I am so happy. I'm going to take a side visit here. I am so happy there are so many students here because it's fun to talk to students because I can say things like orthogonal, and then I can say to you, what the heck does orthogonal mean? Right? Orthogonal means that every year, every month, if you think about like a grid, every year, every drinking water facility, every month, orthogonality means all of those cells would be full of data, right? There would be some data in there. So we have a very nice, robust data set. They took out the drinking water facilities that skipped years. They took out drinking water facilities that went offline for a few months. They took all that stuff out. So they made this ironclad data set where every single cell in the data set is full of data. And we also just looked from March to September because that's the period, that's really the growing season, right? We didn't worry about winter. We just focused on March to September. And within that, in most years, so annually in that, I told you we're making this grid, right? And it's orthogonal. Every cell within the grid has data. Well, how much data? There's about 20 points, 20 data points, 20 atrazine measurements in each one of those little cells. It's kind of a lot of data. It's pretty good. This is what we find. There are real differences. If you live in Illinois, living in Ashland wouldn't be too bad. The red line here is the US EPA drinking water standard for atrazine, which is 3 parts per billion. And atrazine levels in the raw water, not even post-treatment, but pre-treatment. It's going to get better when it goes through treatment, right? Pre-treatment, it never exceeded that 3 parts per billion. I drink that water. Not so much with Mount Olive. Mount Olive, it exceeded 3 parts per billion about half of the time. So every time you're getting a drink out of the water fountain or you're getting a drink from the tap, you're flipping a coin. Do you feel lucky today? Now maybe you think, oh, that's okay. I don't really mind drinking water that exceeds the US EPA drinking water standard, and that's certainly your choice. But is that a choice that we should give people when they don't even know they're getting that choice? That's a little scary. So there's a problem here, right? This is further exacerbated by the fact that these two towns are about 80 miles apart, a little bit further than here to Omaha. They're probably a little closer culturally than here in Omaha, but they're not. That was just a joke. But they're not. I was trying to make a sports reference, but we're better in hockey. You sometimes are better in football, so there's no real good sports reference there. So anyway. 82 miles apart. But really different relative to water quality standards. So in order to understand the health risks associated with ag chemicals in water, we need to know something about, and this is where Dan Snow comes in, my colleague Shannon Bartelt-Hunt, who's also a UNL faculty in civil engineering. This is where some of our previous research comes into play. Right? Because in order to understand why is it that I drink the water if I was in Ashland, but maybe I'd go get a bottle of water if I had to spend the night in Mount Olive. Why is that? Well, it really has to do with the fate and transport of these chemicals in the environment. How are they moving around in the environment? Now, again, if you think about Flint, Michigan, right? Flint, Michigan, that's not a question. That's not really relevant because it's kind of pan city, right? It's kind of across the entire city. So it's not really a relevant question. Here it's a relevant question. And again, I would argue that what that's showing is this is more of a vexing or more of a super wicked problem. You've got a lot of variables that are controlling whether or not the water is safe to drink. So when somebody says, you know, is this a problem? The answer isn't really yes or no like it is in Flint, Michigan. It's kind of like, you got to tell me a little bit more. All right. The signature watershed that I've spent my career, at least in Nebraska, my career working on is the Elkhorn River watershed. This is a watershed that runs from more or less from the outskirts of western Omaha up into up to Fremont, up to Norfolk, then further up into the Sandhills. Sandhills in this little illustration are shown in orange. Corn soybean rotation is pretty much the green. We built, about 5 years ago, we built a little research station. It's about the size of Doctor Who's phone booth from Doctor Who, if you know what that is. We built this little station, and we're able to monitor water quality at this station. And the kind of cool thing is we can have basically continuous water quality monitoring. So because we can have continuous water quality monitoring at this site, we can really get a good bead on temporal changes, the changes in the occurrence of atrazine in the environment over time. Before I go to the next slide, we had to do this because prior to building this station, and Dan Snow was part of this, we would go out into the field, upriver, up into the Sandhills or wherever else, up into this watershed and other watersheds as well. We would bring a bunch of bottles, we would collect a bunch of water, we would bring a bunch of cages, we'd cage fish, we'd put caged fish in the environment. We'd come back the next day and there had been a drought and all our fish were dead, or there had been a flood and all our fish were downstream, down in the Gulf of Mexico somewhere. We had all kinds of problems. Furthermore, we would go out sometimes to the same site. One day we would put out animals, we would collect samples, and there was nothing. There was no ag chemicals whatsoever. A month later, we'd do it again, and the animals were experiencing effects. I'll talk about what effects they had, and there were chemicals all over the place. How come? So we never knew. So we were shooting blind, right? It was like Tom Brady with that last second 2-point conversion. What was that all about? We were like completely like shooting blind. We didn't really know what we were doing. But once we had the station, we were able to be there more or less continuously, and we got a better bead on what's going on in the environment. Now, if you give samples to Dan for the Water Sciences Laboratory to analyze, they can do a really good job on that. And they will come back and they will tell you what the concentration is. And that's really, really good. The problem is it's not going to be today. I mean, if you give it to them at 8 this morning, it won't be 5 tonight. And it may not be tomorrow. And during the busy times of the year, it may not be next week. It may not even be next month, right? Because there's, you can imagine, there's a lot of people doing research. There's a lot of samples they have to have passed through. It takes time. But we want to know. I'm an impatient guy. I don't want to wait a month. I want to know what's going on in the environment now, like now. So one thing and this was a conversation that Dan and I had over a beer at a scientific meeting. I said, we were sitting there waxing poetically, and Dan was saying, I'd really like to have a date with Catwoman. And I said, well, I'd really like to have a strip where I could measure atrazine. That's the way Dan and I think, we just think about different things. So I was like, I'd really like to have a strip where we could measure atrazine in the field. And Dan said to me, that exists. And I was like, no, really, Dan, I'd really like to. And he's like, no, seriously. That night, he sent me the URL. I went to the page, and there it is. So we can get these strips. It's like a pregnancy tester. How many of you have used that? No, you don't have to raise your hand. It's like a pregnancy tester or an ovulation strip, or like, it's not really blood glucose, because pregnancy and ovulation strips are yes, no. You're either pregnant or you're not. You're not like a little pregnant. You know, you're either yes, no. I mean, there's no, you know, to the dismay of many young couples, it's a dichotomous situation. It's the same way that these strips work. 2 strips, 2 lines here. Yes, we have atrazine. The rabbit died. 1 strip, no, no atrazine. Really easy to read. These things cost $10. They take 10 minutes to incubate in the field, and they discriminate at 3 parts per billion. So they're discriminating at the US EPA standard. And also, if you look on there where you see that ET in the green check, these are EPA test verified. So this has been validated by the EPA. So this is serious stuff. For $10, you will know whether or not the water sample that you have exceeds the US EPA drinking water standard for atrazine or not. And this, I was telling you before, there's a reason why we use atrazine. This is why we use atrazine, because we have this little tiny strip that can tell us something very, very specific. Now that specificity becomes more important, and I'll talk about that in about 5 minutes. All right. So now we can go to the field and we can, and again, I know that some of you are in science or in environmental science or environmental studies. We can do what's known as stratified random sampling, right? What does stratified random sampling mean? Well, you want to, you know, what everyone tells you in science is, right, is randomize. You don't want to bias your data. Have things be random. Well, what does stratified random mean? If I tell you that that sometime during today, I'm going to start throwing $20 bills off this stage, and I'm going to do that once a minute for an hour, you would probably be interested in being here. But you don't want to sit in that chair for 24 hours, right? So what you would do is, at the top of the hour, you would come in and you'd look in the door, any money? No, no money, and you'd go away, right? But then when you started seeing me flipping bills, you'd probably stay here for the entire hour, right? So you stratify your sampling, so you focus your sampling when there's something interesting going on, and you don't have sampling when there's nothing interesting going on. So that's what we were able to do. And I'm sorry I skipped a slide. I will show you that in a second. The other thing that we were able to do at the station is we were able to go out with one of these strips because they're cheap, so you can get a lot of samples because they don't cost very much. These samples cost about 1/10 of what it would cost to send a sample to Dan. Again, Dan gives me a whole bunch more information, but right now I'm not interested in quantification. I'm just interested in yes, no. Is there atrazine exceeding the US EPA standard or not in the water? Yes, no, that's all I'm interested in. So that's what this is showing. This is showing 5 years worth of data from 2011 to 15. The blue is no, the green is yes, April, May, June. The chemical, and the 2 things pop out. The chemical's there in May, it's not really there in April, it's there in May, it starts to go away in June. The second thing that pops out is there's no week when every 5 years it was there. So it varies, there's temporal variation. How come? How come it's varying all over the place? Okay, we know why. And the reason why, this is a figure showing time relative to river discharge. River discharge, just the cubic feet per second of water moving down the river. River discharge is driven by rain. Every time it rains, discharge goes up. So these peaks that you see are rainstorms, right? Or they're the product of a couple of hours after rainstorms. And what you can see here is that early in the year in April, oh, one other thing, the red diamonds, no atrazine, green diamonds, atrazine. And what you can see is early in April, we're not getting any hits. Then we get a rainstorm, we get runoff, then we get a bunch of green hits. Then they go away, they move downstream, we get a couple more red hits. Then we get another rainstorm, we get a couple more hits. And so the pulse is based upon rainstorms. We've known this for a while. Some of Dan's early work and some other people from UNL's early work has shown this. People have known this for years. But now what we can do is I can go out to the field without worrying about the weather and in 10 minutes tell you whether or not we're in one of these events. Because we have these episodic events, and it's really important for us to be able to know when the events occur. Prior to the advent of these strips, like I was told you before, we were flying blind. We had no idea whether the event was there or not. Here's another year. This year's a little different, right? This year, we don't get any hits, and then we get a rainstorm, and then we just get almost like continuous hits. Well, how come? This just happened to be a really wet year. So it was dry, the farmers applied, then it got really wet for a really long time, and it was there all the time. I told you before, another really nice attribute of the atrazine strip is that if we look during one of these periods when we're having positive hits, we don't just see atrazine. I'm not here I'm not trying to make any indictment on the specific chemical. I'm really not. But what we're seeing is we're using atrazine as a surrogate chemical. It's indicative of the movement of a whole bunch of chemicals. I don't care about the player. I used this analogy once. People liked it, so I'll use it again. Right? We have the usual suspects. Whether we have the lead individual, whether we get the lead individual or not, doesn't matter. When the lead individual shows up, all his henchmen, it's like the old Batman show, right? Every time the Joker showed up, it wasn't just the Joker by himself, he had all his henchmen with him, right? So every time atrazine shows up, it's not just atrazine, all his henchmen come along. So we're not really specifically concerned about the individual chemical, we're concerned about the mixture. And what that little strip tells us is, yeah, atrazine's here, and he's brought his friends. So during one of these pulses, we see atrazine and his pals. During one of these non-pulses, for all practical purposes, we don't. It's kind of cool. Furthermore, again, for those of you who are a little more mathematically inclined, right? If we look at a correlation matrix. So this is just the correlation between atrazine and the other chemicals, or the other chemicals and themselves. Perfect correlation would be a value of 1. So the closer these numbers are to 1, the better the covariation. And look at these numbers. They're all 0.9s, 0.8s, a couple of 0.7s. And they're all statistically significant, meaning, again, when the Joker shows up, he's got his suite of henchmen with him. I don't care about the Joker. I care about the whole. I don't have to just take on him. I got to take on everybody, right? It's not, you're not just going after the ringleader. You have to take on the whole gang, right? So again, I am not up here trying to implicate any individual chemical or anything like that. This suite, what does this do in drinking water? I'm not drinking that. That's scary to me. No thanks, I think I'll pass. Mount Olive, not so sure. Not so sure I want to drink your water. These chemicals are not benign, and I can show you real quickly that they're not benign, because we are able, again, since we can now pinpoint pulses with these rapid strips, we can now only deploy, we can randomly stratify our sampling such that we bring animals to the field when the field is hot, right? So what we were able to do, as you can see here, we brought fish to the field into the station when the field was hot, when the chemicals were there. And what happens? I'm not going to go, for the sake of time, I'm not going to go into this, but the animals experience endocrine disruption. This is a female minnow here, and after her 7 days, she's less female. I don't think any of the females in the audience would volunteer for that, and I don't think any of the males in the audience would date this fish. She's just less female. And it's because she was exposed during that 7-day period. We know that because if we look at another 7-day period, post-pulse, right, and we put fish out here, they're fine. No difference. They're fine. They're not defeminized. They're just fine. So the chemical has an effect. Not the chemical, the mixture of chemicals has an impact. And again, that's why I wouldn't drink that water. And again, I recognize we're talking about raw surface water, but that raw surface water, just as a sidebar, in Illinois, in that study that the US EPA did, there was a very strong correlation across those 15 different communities between surface water coming in and drinking water going out. Yeah, the drinking water facility remediated the level a little bit, but the drinking water facilities that had high atrazine coming in had high atrazine going out. It was lower than it was when it came in, but it was still high. The ones that had low coming in had low going out. So it's not just a raw water and drinking water is fine. It doesn't work that way. All right, so kind of in summary from this part of the talk, temporal variation, atrazine is present in pulses that depend upon storm events. The presence of atrazine is indicative of the presence of a suite of ag chemicals, so we're not picking on any given crop or any given specific chemical or any given Syngenta or anything like that, any specific company. We're interested in the suite of chemicals themselves. These chemicals are biologically active and they do create adverse health impacts. And all you have to do is put a fish in our station for a week during a pulse and you can see it for yourself. All right, so we've talked a little bit about spatial variation. I'm sorry, this slide is wrong because what I wanted to do is I now wanted to switch over and talk about, no, I said that right. I said it right the first time. We talked about temporal variation. Now we want to switch over and talk about spatial variation, right? Variation across geography. Kind of getting back to that Illinois question of why Mount Olive and why not Ashland? And here is where, as Dan was saying, here's where we can actually evoke citizen scientists. This strip is so easy to use that I could give one to your kid brother in high school and he can go out and do this in Salt Creek or wherever he wants, Platte River or wherever he wants, and he can generate realistic data. And then he can email that or go to our website and upload that data, and we'll incorporate that into our database. We did that in 2011. We used a bunch of Boy Scout kids. Full disclosure, my son was a Boy Scout at the time, so I had kind of a captive audience. We went out, we collected 100 data points in one day up and down the Elkhorn River. The Elkhorn River is a 10,000 square kilometer watershed, 320 linear miles of river, so it's reasonably large. We couldn't have done that just with a pickup truck and a bunch of graduate students. That we would have never been able to get that many samples. So by using citizen scientists, we were able to really increase our sample size. So we mailed them out the strips, we sent them strips, people went out, they did the thing, they sent us back the data. It's really cool. And again, we used a whole bunch of volunteer organizations, schools, Nebraska Master Naturalists, Sierra Club, Keep Fremont Beautiful, Keep Norfolk Beautiful, the whole 9 yards. So we used a whole bunch of people, got them out there, did this work. They enjoyed it. We enjoyed it. It's really cool. I don't have the slide anymore in here because I took it out. There was a slide that I had of an email that someone sent me, and they said, you know, I really enjoyed doing this, so blah, 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 blah. Tom Smith, comma, citizen scientist. He was calling himself a citizen scientist. How gratifying is that? That's like so cool that not only is this guy importing data into our database, but he's actually like taking ownership of the name. You know, pretty neat. Here was our little website that we used. It's not really important at this stage of the game, but we had an interactive website. You could go on, you can input your data. It was really easy. I'm sorry, this slide shouldn't be here. I apologize. So let's take a look at the data. So here's the data in the Elkhorn River watershed. 96 tests over the course of one day. So this was all collected on the same day. Western Nebraska, nothing. How come? It's sandhills. They don't have corn up there. So we don't see any atrazine. Really nice control, right? A really nice place where you shouldn't see it, and indeed we don't. And it's not we didn't, the citizen scientists didn't see it. Down around Fremont, it's coming in about 30% of the time, 1 out of every 3 sites. Down here, as we get closer to Omaha, about almost 3/4 of the time, we're picking up atrazine. It's really nice because it makes a really nice story relative to the geography, because this is exactly what you would expect, right? As water moves from the relatively clean sand hills down through corn and soybean country, you pick up corn, soybean, ag chemicals. Exactly what happens. Really kind of cool. can we take this, the little pink oval here is the Elkhorn River. And as we were talking about before, I think water contamination on the level of the Missouri-Mississippi River, which is one of the top 10 in square mileage river systems in the world, certainly the largest in North America, I think this is a super wicked problem. But thus far, we've only captured, or we've only talked about one little tiny geography. Can we get bigger? Can we get more ambitious than that? Can we take this idea of using a relatively simple metric, giving it to citizen scientists, and covering the whole watershed? Yeah, that's us there. That's Elkhorn River there. So can we do that? That's what Little Miss Atrazine, Dan was talking about the citizen science project that I run called Little Miss Atrazine. That's what Little Miss Atrazine is all about. So we're going to look at New Orleans, Arkansas, Ohio, St. Louis, Missouri, Minnesota. We're just going to take it all, take the whole thing. Can you do that? Is that really possible? Yeah, it's possible. So here's the data. Here's the data that we collected. This was back in 2014. And again, all of these samples that we collected, it doesn't look like much because the number of these samples are fairly superimposed on top of each other because the dots are large and the map is obviously small because we're talking about the entire width of the United States. All the samples were collected on a 24-hour period on June 7th, 2014. We collected 211 usable data points collected from seven states, starting at Lake Itasca, where I sampled. Why did I sample Lake Itasca, Minnesota? The fishing up there is really, really good. So you go up there, you spend 10 minutes collecting an atrazine sample, and then you fish for 3 days. It's not bad. So we have Lake Itasca, which is way up in the upper part of Minnesota, and we collected, which is actually the headwaters of the Mississippi River, and we collected all the way down to New Orleans. And this is what we found. The far north, really Minnesota, we didn't see any atrazine at all. The north part, northern Illinois, we saw it about 10% of our samples. The ends are our sample size, right? So we have a fairly good sized sample from Minnesota, about 23 sites. Northern Illinois, we have about 60 sites. We've got a lot of volunteers from around the Chicago area. Even though that's not exactly on the river, it's still in that overall area. And there's once you get out of the Chicago metropolitan area, you've got corn soybean rotation in there. So we figured that was fair game. But once you hit St. Louis, start picking up a fair amount of atrazine. And then when you get a little bit south of that, when you hit the Kentucky-Missouri border, you start picking up a lot of atrazine, about 50% of the samples. And this is 37 samples, so it's not a trivial sample size. About 50% of the samples are indicative of having atrazine in the sample that the people collected. So we're getting this geographical gradient of atrazine up and down the entire United States. Up in the north, not so much. Down south, not so much. Right smack in the middle, boom, there's all this atrazine. This is a map of atrazine application, where the red is the most intense application and the white is the least intense application. And I've superimposed upon that the sites where we actually collected samples. Or excuse me, the sites where we collected samples and had the really high levels of occurrence of atrazine in the surface water. The thing that may not stick out, that may not be obvious to you, so I will point it out, is the boundary between Illinois, Indiana, and Kentucky. This boundary is the Ohio River. And the boundary between Iowa and Missouri and Illinois is the Mississippi. So what we're seeing is we're winding up right where all the big rivers that effectively, and then of course you all realize that Nebraska, Kansas, Iowa, western Minnesota, western Missouri are all draining through the Missouri, which cuts this way, right? So this is ground central, right? All of the water, the watershed that drains virtually this entire region that's red, all of that water drains through those, not all, probably 80, 90% of the water that drains that area is coming right down that chute. And that's where we're seeing the incidents. Now, at that point, I get kind of excited. And there was a recent study put out by the Environmental Working Group that has similar maps to this that have been done professionally with professional scientists going out and collecting water at drinking water facilities. I'm not going to show you that map, but they found basically the same thing, right? They found basically that kind of as you move down these tributaries towards the main stem of the Mississippi, the occurrence and the exceedance of the 3 parts per billion of atrazine goes up. It's kind of interesting. And again, at this point, I get excited and I take off my aquatic biology hat and I put on my public health hat. And that's, for good or bad, the end of the story, because the answer is I don't know. But it sure is an interesting smoking gun, because this area where these major river systems are coming together is hot. And how hot is it? And is it hot enough to be a problem? We don't have an answer for that. But we do know that there are multiple lines of evidence that are suggesting that this area is hot. I think that's really interesting. Again, we're talking about a large geography. We're also talking about effects that are subtle, not children having neurotoxicity. This is a really difficult problem to address. And it's also a really difficult problem to make people even understand or believe it, that it is a problem. But I think, again, putting on my academic hat, I also think it's just really, really interesting. And my, to wax a tiny bit poetic, my career resurged when I joined the College of Public Health, because now I was able to take all this stuff that I knew about biology, and not that I know that much, but all that stuff, this stuff I know about biology and water chemistry, and I was able to bring it into the public health arena. And it's just been really, really fun since. Yes, here's the major river systems, the Ohio, the Mississippi, and the Missouri, and they're all converging on that ground zero. Really kind of cool. So from the temporal perspective, within a single day, atrazine concentration varies considerably from site to site across the largest geography you can possibly have in North America, right? From Louisiana to Lake Itasca. It doesn't get much bigger than that. That transcends effectively all of corn country. Also, while our results are not potentially earth-shattering, it's not like, gee, how could anyone have come up with that? It's not like this leap of faith or anything. It's really interesting, because this is the first time that this simple little tool that we have has allowed hundreds of people to go out and do simultaneous measurement. Now, I was talking with the professor who's here from Nebraska Wesleyan, and he was, and he was saying that there are some of you here that are interested in environmental studies, and that while you may not be the hardcore scientists in the lab, you're kind of interested in potentially ideas like this, and you would be you might wind up as individuals who would be managing projects or managing how communities interact with things like this. The point is that cell phones have revolutionized the world. And if you don't believe that, just go back a couple of years and look at Arab Spring, right? There is the New York Times photo of the year a couple of years ago was the Libyan refugees that were homeless, that had left Libya. This was a number of years ago, but the Libyan refugees that had left Libya, these guys are homeless, and they're on a beach, and there's 20, 30 guys, and they're all standing trying to get, and I'm not making this up, they're all standing trying to get cell phone connection. Cell phones have revolutionized the world because we have immediate access to both data acquisition and data acquisition in both sense, right? You can acquire data and transmit it into a database. You can also look at that database and bring that data down. You don't need me, you don't need Dan, you don't need your professors, it's you. I am super excited about that. Because what it does is you can sit here and there may be multiple things that I said where you're like, that, yeah, you make a nice story and you got a nice way of talking and, that's really nice, but I'm not so sure I believe you. You don't have to. You can actually be part of the data generation itself, and then you can look at the data and make your own determination. You can be that empowered. And if you think I'm giving you like a soft soap and like I'm not making this up. Like that can really happen. That's our goal. That's where we're really heading with this, to empower you. Because, Dan and I are old guys. We're not going to be here that much longer. You guys are going to be here for a while and you're going to have kids, right? So you're going to be the inheritors. You should be involved in the decision-making process. And I can get you, I can get you there because I can get you involved in this project this spring, if that's something that you would be interested in, and it's okay if you're not because we have tons of volunteers, but you have that power now to be involved in this stuff. And the title of this talk was what water and health issues and opportunities. And I'm talking to the undergraduates in the audience between 19 and 25 years old. You now, not when you graduate with your PhD, not when you get a job with Nebraska DEQ, you now can be involved in that process. You now can take advantage of some of those opportunities. Kind of cool. Certainly not something that was available to Dan or I when we were at your age. Yeah, so just kind of summing up, the spatial and temporal relationships between atrazine application and detection in surface water are reasonably well understood. Efforts are underway to elucidate the relationship between surface water incidents and adverse health impacts, and you can actually help with that, leading to a healthy community. I'm just going to take a couple more seconds. I started out as a hardcore biologist, like hardcore benchtop biologist. I have students in my lab who are hardcore benchtop biologists. I never thought I was going to wind up standing here saying you can make a difference to generate a healthy community. It's just kind of cool, but it's actually happens to be true. All right. I've worked with a bunch of collaborators. You can see Dan's name on here, Shannon, a couple other people. I've had a bunch of graduate students, had a whole bunch of undergraduates helping out with that. And we've had a bunch of partners all over the state and agencies and stuff like that. So with that, thanks for having me. And I both welcome your questions and also I welcome your participation if you're interested.
Is this going to be online? I better say hi, Mom. Hi, how's it going? But on a more scientific note, kind of a couple slides back, you talked about the numbers and where the atrazine atrazine came up in the samples. And I was wondering if you had any thoughts on why there, and I know it was a small sample size, but why there were none that tested positive in Louisiana.
Yeah, that's a really good question. And our a priori hypothesis would have been that the river would light up, let's say in St. Louis, and it would stay lit up all the way down, and it doesn't. And if you've ever been to St. Louis and New Orleans, you know that the Mississippi River's a heck of a lot bigger in New Orleans. So a piece of it could actually be, I'm going to use the phrase even though I don't believe it, the solution to pollution is dilution. It could just be that it's getting diluted out because there's so much more water there. But the other thing that's happening is, and this is another talk. So when I come back next week for that talk, I'll give you this one. And that is that water moving downstream is not in a pipe, right? It's not the Flint River drinking water facility. It's in the environment, meaning that a molecule of atrazine is bouncing around. It's bouncing into a sediment particle where it may adhere. It's interacting with microorganisms. There's a lot of that molecule of atrazine is in peril, right? It is in peril of sticking to a sediment particle where it would be taken out of solution. It's in peril of going into a certain type of microbe that can break that atrazine down. So just because there's atrazine in the water doesn't mean that it's necessarily safe traveling all the way to the Gulf of Mexico.
Thanks very much for the talk. A comment and then a question. Of course, we're looking at one particular class of pollutants, and by the time you get further south in the river, we've got oil refineries and lots of other issues going on. And I'm pretty familiar with that with pharmaceutical pollution in the Musi River and outside Hyderabad, and how that plays out. From your perspective, if atrazine is there in high levels, and if it's documentable in high levels, and yet the EPA study in Illinois shows that the clean water on the way out is still retaining high levels, can you talk a little bit about, well, why isn't the purification process or the cleaning process more effective if we know that something like that is there?
Again, I'm happy to talk about it, but and I think this is really kind of hopefully interesting relative to the students, because again, I think what it illustrates to you is that there's a book that just recently came out that's called The Rambunctious Garden, and it's the fact that they're really, I'm going to paint with a really thick brush, but this is what the book says. There really is no wilderness left anymore. What we have is we have really rambunctious gardens. We have wilderness areas that are managed by humans, right? But they're not really pure wilderness anymore. That's gone. Human impact is absolutely everywhere, all right? So, and that's kind of important. Now, I'm sorry, would you just kind of ask me that question again? Yeah, and thank you. And the reason, there's a bunch of different reasons for it. And we start getting back to the Flint, Michigan reason. Mount Olive, and I'm not picking on them at all, but I'm using them because I've already showed you the data. Mount Olive is a community of 2,500 people in central Illinois that farm and ranch. These people don't have a whole lot of money, right? When was that? And I don't know this for a fact, but I would wager that their drinking water facility is not new. It's not using the state-of-the-art technologies. Where are they going to get the money for that? How are 2,500 people going to put in a $20 million drinking water facility? So the technology may be there, and this is the point about the rambunctious garden, right? There is no such thing as we have biology or nature or wilderness or ecosystem, and then we have Omaha, Lincoln, human civilization, right? It's not like that anymore. The two have interdigitated with each other, and that's the whole point, that science has become transdisciplinary. Dan and I can do all the natural science. Dan can do the chemistry. I can do the biology. We can do all the natural science we want. But if we don't have social scientists that we deal with, and by social scientists, I'm talking about not only social scientists, but also people like economists and politicians and government officials, if we're not talking to them, then just like Pontiac, Michigan, it's no longer a biological or science question. It's a social question. It's a political question. So the answer, and I recognize this is a long-winded answer to your question, but the answer is that these problems have become an interdigitation of science with politics, or science with social science, right? And again, as I pointed out relative to your students, even if you don't see yourself at a benchtop doing the water chemistry, being involved in the economics of clean water or the politics of clean water, there is room for you there. Absolutely.
All right, well, I think we'll have to let that be the last question. If you have questions for Alan, he'll be around after the seminar. Thank you.